Okay, today we want to talk about score matching. Score matching would be score matching can be also in the next part. For example, diffusion. We can start with the score matching our diffusion part, but because of the connection between energy-based models and score matching, I decided to have them here, and we have a smooth transition from energy-based model to diffusion using score matching. Okay. You will remember that we have a very flexible type of models, the energy-based models. They were very flexible in terms of selecting the architecture, and we see that but they have some severe problems in generating samples from the model, because you just have this type of mapping. There is something that if you give your model X, it will generate something like this, but we see that we cannot have the normalized distribution here, so we have an unnormalized version of your distribution, and because you do not have the normalizing factor, that we call it partition function, there are challenges in sampling from this type of model. We see two methods to sample from it. Then we talk about how we can train it. Training the model needs sampling from the model and estimating this expectation. But the problem is that the sampling is very hard, so we need to replace this idea. And our replacement option was contrastive divergence. And you see that in contrastive divergence, you can have this type of loss function. It means, it means that instead of sampling from the true model distribution, you just need to sample from model distribution in a specific iteration of your sampling procedure. And you can simply select t equal to 1, and you just need one iteration using, for example, Mala to generate samples from this p theta t of x. So it simplified the training. And we see that this type of loss function can have some intuition toward preserving the area on the curve. It means that you increase the area for the places that you have samples, you have training samples, increase here, and also decrease in other parts of your model distribution at the iteration. Just one question. Assume that the model is somehow trained. The model is somehow trained. How do you interpret this increase and decrease in a trained model? In a trained model, what happened? Assume that you have two training samples here and here, and a trained model is something like this, because it is trained. Okay? What happened, do you think? One of this direction wants to increase, for example, here. One of them want to increase. One of them want to decrease. So they cancel each other, and it is that your model is trained. Does it make sense? This is just idealization. We know that they are not working on the same point. They are different samples. Okay, maybe you sample from the model, and the result of model is this point, and you sample from the data, the result of data is this point. So they act in the different directions. Okay, but in the average, what happened is that nothing will be changed. Okay. So this was the contrastive divergence. Now we want to talk about a new family of algorithms that you can use to find the score function. I will define the score match function explicitly in this part. Any question about CD, contrastive divergence? Okay. Till now, we have different models. Some of them are trained using likelihood-based training, such as deep autoregressive models, variational autoencoders, normalizing clue, and some of them are trained based on without likelihood, means such as GAN. In GAN, you do not calculate p theta of x anywhere. You just have some samples, and you have a critic, and the critic decides whether you are generating good samples or not. But in EBM, we see that CD is a type of likelihood-based method. But in general, to use the likelihood-based methods, we need to calculate the partition function, which is intractable. CD mitigates the problem in some ways, but it has some approximation. You see that there was an integral term that we deleted and result in an approximation. Also, unlike the likelihood-free methods, in likelihood-free methods, for example, in GAN, you can easily generate samples. You can easily generate Z and then pass Z through your generator, and you have samples of your model. So generating samples in that model is very easy. But here, still you cannot generate samples easily because you need to run a Markov chain Monte Carlo method. So they have a problem both for likelihood-based methods and for likelihood-free methods, the energy-based model. Okay? Does it make sense? Why both of them are challenging for energy-based model? The likelihood is challenging because you cannot calculate partition function. The likelihood-free is challenging because you cannot easily sample them. So both of them are challenging here. And we should find a new way of fitting these models. So we see that CD is an alternative. It is likelihood-based. It is to somehow likelihood-based. But in this part, we will talk about a new framework of fitting such models. The intuition again comes from this this notation. We know that the distribution, the normalized distribution, is the exponent of minus energy divided by the partition function, and the partition function is the integral of the exponent of minus energy. If you calculate the gradient of the log of the model distribution, you will see something which is independent of partition function, and this gives you some signals how to get rid of the partition function. The problem is the partition function. The problem for the likelihood type is the partition function. You cannot calculate it. But if you have something about the gradients of the log of the model and PDF, then you have something which is independent of the partition function. So this is the main definition here. S of x, S is bold, so S is a vector. S of x equals to minus the gradient with respect to the x of the energy is known as a score function. And we have previously used it in LMC. We see that in LMC, the direction was the result of the minus the gradient of the energy. So we previously used it, but we do not have an explicit name of score function for it. So from now on, we use the score function definition for this value. One important point, the score function is a vector. The score function is a vector of what dimension? X. D, the capital D. So we want to switch from working with P of x to working with S of x, which is a vector. Okay, but what is the important point about the score function? Score function and PDF are alternative representations. What does it mean? It means that if you have a score function, it means that you potentially have the PDF, and if you have PDF, you can easily derive the score function. So they are alternative, and the information is similar in both of them. It means that if you have a score function, you do not miss any information about the density. Every information is inside the score function. Why is the case? Why is it the case? Because if we know that if we have the gradient, we may miss some constant. You know that if I have x plus c, and then I take the gradient of this function, I have 1. If I excuse me, x plus 10, okay? If I take the gradient, I have 1. If I take the integral again, I have x plus a constant. But this constant is missed. I cannot infer that just by having this 1, I cannot infer that this constant is 10, okay? But in the probability and in P of x, we have a property. What is that property? Yeah, it is the area under curve here is equal to 1. So this constant should be selected such that the area under curve is equal to 1. So just for the case of the probability, we have this property that these are alternative representations. It means that no information is missed when you switch to the score function. Okay? So while P of x is a scalar, S of x is a vector with the same dimension as x, we know that. But let's see the score function for the simple case of a Gaussian distribution. Assume that I have a Gaussian distribution with mean mu and variance sigma 2. What happened for the score function? The score function is the gradient of this, the log of this function with respect to x. And you can see it is a very easy formulation for the score function in contrast to the distribution itself. And you can also recover your distribution using the score function. And we know that in the case, you do not have any missing information because k can be calculated easily due to the fact that P of x is normalized. Okay, k can be identified. But let's think of this score function in terms of figures, okay? Here I plot, I have a mixture of Gaussian. The formulation of the mixture is written above. And I calculate the score function in each point. We know that for this curve, the score function is of dimension. And for here, this is 1, because this is x is 1-dimensional, okay? The score function is a number, whether positive or negative. The direction of these arrows show that it is whether positive or negative, and their length is representing the amplitude of the score. If it is a big arrow, it means that the amplitude is large, the amplitude just. For example, here is very large, here is large. When it is a small arrow, it means that the amplitude is very small. Okay? What do you think? Where are they pointing to?
0, 4.
Where?
0, 4.
Yeah, and what are those points? What? Yeah, they are pointing to the high probability regions. They are all pointing to high probability regions. If you are far away from that high probability point, they are very large. If you are near, they are very small. they have very intuitive interpretation. You are pointing to the maximum likelihood. You are pointing to the area where you have the maximum likelihood. And when you are coming near and near to that point, their amplitude is decreasing. In the marginal case, if you are at the point, at this peak and at that peak, what happened, do you think? What do you think? We are exactly at the local maximum. What happened? They are 0. So you have some interesting indicator of the maximum likelihood. If your score is 0, you are at the maximum likelihood. At least local maximum likelihood. It means that in both of these points your score is 0. But you can understand that you are at least at the maximum in your neighborhood region. Okay, does it make sense? So a score is very interesting metric, and it can be an alternative to the distribution P of X, PDF. Okay? So let's recap our big picture with the scores. Previously, we have this image with P of X and the family of the distributions. Now we want to switch from the P of X to score. Okay? The complete family, assume that I want to find a distribution. I want to find P data of X. I know that the true distribution that I do not have access to is equivalent to a score function. I know that this score function is of dimension D, but this is a real number. Okay? So, I can consider that there is a complete family of score functions related to my data, related to the dimension of my data, and one point is the best one among those points. Okay? There are lots of score functions here. One of them is the best one for me. Then, instead of characterizing my family in terms of the probability PDF, I characterize my family in terms of the score functions. I select a family of score functions. And then, what happened? I design my distance based on the score functions instead of the distributions. Previously, we designed it based on the KLA divergence. Now, I design it based on the score functions. What is the difference? The distributions are numeric values, are of dimension 1, but here you should compare two vectors. It may have some problems. This L, this distance at the inputs accept two vectors and should work under vectors. Okay? Anything, we do not design it yet. Yeah. You will see that the first one is the L2 norm between two vectors. Very simple. And here it makes sense. Okay. So then what happened? I start to minimize this distance between the score of two distributions, the score of your model, score of your data, and then find something which is theta star, which is the best member of my family that has the nearest distance to the true data score function, not the true data mod, PDF. So, assume that I train this model. What happened? At the end of the day, I have S theta star of X. What can I do with S theta star of X? One approach is to recover the PDF, but that's very hard. Why? Because to recover the PDF, you have some problems such as partition function calculation. But in most of the problems, you just need to sample from the model. For example, in conditional sampling models like diffusion models that you worked with them today, you just sample from the model. And this is enough information to sample from the model. You can easily use it as the input to the model, to your sampling, to your MCMC, and then the MCMC will sample from the model. And you will have generate samples from the distributions. You may not be able to calculate the likelihood of a data point, but instead you can easily not. You can sample from that one. Because sampling is also hard. You need to converge model, and then you have a reliable sample. But it is an indicator. It is something which is highly related to your PDF. We know that in some cases you can easily recover your PDF. Yes.
You mentioned that the score function and the corresponding distribution are basically the same.
Yes.
So why did you say that it's hard to get the PDF?
Because of the integration. You need to integrate the score function. Integration is intractable. Yeah. This integral is very hard, but we know that S theta star of x is enough in most of our applications, or at least it can be very useful. Okay. So we want to shift our viewpoint to learning, from working with PDFs to working with score function. And we want to design networks for a score function, not for the PDF. Okay, let's talk about the challenges. The first one, KL divergence that previously used as this L was a metric that compares two scalars, but now we should compare two vectors. This is the first challenge. And what is the dimension? Assume that you are training on ImageNet. The dimension is very large, 2024 times 2024 times 3, for example. The next one, in theory, S of x and P of x are equal, but computing P of x from S of x needs a similar procedure as calculating the partition function. So you usually cannot recover the PDF using the score function. You just fit the score, and you know that it is equivalent to the data PDF. The next one, score matching, needs the calculation of the gradient of P data of X, which seems challenging as we just access to samples from P data. This is the severe problem. You have just samples from the P data. Now you should be able to take the gradient of that distribution. The distribution which is not clear. What is the P data distribution? This is something that you want to estimate. Now you should take the gradient of that function, because you want to fit the scores. So you need the reference. The reference is this one. The reference is the gradient of the true data distribution. And you should match to that reference. This is the most challenging problem. So previously you do not have P data, you just sample from it, for example, to calculate the callback-Livler divergence. Now you should take the gradient of something that you do not know. It is very challenging, but we see that it can be mitigated with some tricks. Okay, but pay attention. This is the most important challenge at the first glance. This is the most important. The model to estimate S data of X is a mapping with dimension RD to RD. Thus, it is not as simple as an EBM. EBM is RD to 1. This is RD to RD, which is much more challenging. For example, you have 1,000 by 1,000 images. Then this dimension is 1 million to 1 million. Very challenging. Okay, even if you train the model and you calculate S theta of X with any method, then for sampling you again need something like LMC. MH is not suitable here because you do not use the information. You need LMC. And Langevin Monte Carlo, and we know that in Langevin Monte Carlo we do not know when the the sampling methods converge, and you may need lots of iterations to sample from the model. And calculating the exact likelihood is also intractable because the integral that we talk about is intractable. So you may not be able to calculate the exact likelihood of a data point. For example, in some tasks like outlier detection, but you can change the outlier detection task such that you can use the score function instead of the value of the probability. What do you think? Assume that I want to use the score function in the task of outlier detection or out of distribution detection. What can I do instead of p theta? I do not have access to p theta, but I have access to p s theta of x, s theta of x. Previously, I can threshold on p theta of x, and then I can reject some of the samples. Now I have s theta of x. What do you think? How can I reject the outliers using s theta? Exactly. You can take the magnitude of s theta of x because the magnitude show that how near you are to the maximum of the maximum likelihood, the local maximum likelihood. So if this magnitude you train it on some data that are in layer, and then you can find the outliers. The magnitude of this s theta is an indicator of whether that data is in layer or outlier. Does it make sense? Any question? Okay. And also the last one is that you do not have any definition for the latent representation now. You do not see any latent representation. We will see that in diffusion you have some latent representations, but those latent representations are similar to flu models. It means that they may not have attribute vectors. But in the naive formulation, you do not see any latent representation. Okay? So these are the challenges with score matching. Now we want to take steps toward practical definition of that loss. How can we define the loss function for score matching? Himarinen and Dayan, this is a very great paper. I strongly recommend you to look at this paper. This is very well written and very intuitive in terms of score functions. Okay, they proposed to use the expected square distance between the model score function s theta of x and the data score function s theta of x, also called the Fisher divergence or explicit score matching. So these definitions are very important from now on. The first one is explicit score matching, okay? The explicit score matching is you naively compare the score functions of the model and the data, okay? Oh, we have something here. Let me write it here. L of explicit score matching of theta. So that 1/2 is just for the calculation of the gradient. It's not very important. X coming from P data of your model scores minus your data score. It is very trivial loss function. It said that look at your data. Look at the probable points in the data. It means that training data. Data coming from P data is training data. Look at those samples and calculate the difference calculate the expectation of the difference between the model score there and data score there. It means that assume that you have two-dimensional data. They are, for example, scattered like this. Okay, these are the data samples. It means that it is not important how these two values are related in low, let's say, density regions. It is important how they are compared, and how is their distance in high density regions. This indicates the high density regions, and this calculate the difference. Does it make sense? The loss? Does the loss make sense? Because it is very important to understand this loss. We look at the high density regions in the data distributions and compare the two score functions. One of them is your model, one of them is your data. We do not know what is data. We cannot calculate it. We know that there are lots of challenges inside this term. But just as a distance, does it make sense for you? Okay. One of the very interesting point that Hivarinen and Dayan shows, they define implicit score matching, ISM, as this one. Equals to, again, the expectation is with respect to data coming from data. Look at the term, then I want to ask you a question. Look at the loss. What is the term you are taking the expectation with? The trace of the gradient with respect to the x of the model. What happened? We do not know. Why is this loss important? This is not meaningful, even for me, in the first glance, okay? It is not meaningful. But in terms of calculation, what do you see in this term, in terms of just calculation? S theta of x, one important point. S theta of x is a neural network, okay? It is input with x1 through xd, and then output something like S theta of x first until S theta of x last. So this S theta of x is a neural network with RD input and RD output, so it is very simple. A neural network with the same dimension of input and output. In terms of calculation, is this loss, can you calculate this loss? Don't pay attention to loss. This term, can you calculate this term?
The first term?
What?
The first term comes from the...
if I give you samples from P data, can you calculate it?
The gradient?
No, just calculate it. You know, for the first one, calculation is also impossible because you do not have access to S data of x. What is S data of x? We do not even know what is P data of x. We just have samples from P data. But in the first one, you cannot even calculate it because you do not have what is S data of x. If you even sample from P data, which is very simple, you cannot calculate this difference. Because what do you replace S data of x? You can replace S theta of x using this network, but you cannot replace S data of x. What is S data? You just have samples from P data. Look at this. You have P data. If you have P data in explicit form, then you can calculate S data. But you do not have it in explicit form. You just have sample from it. You have just samples from P data. So what happened? How you can calculate it? What about the second one? What do you think? Can we calculate it? Just calculate.
Yes, I think you can calculate it because you have control over S of theta.
Yeah, both of terms are in terms of S theta. Both of terms there are in terms of S theta. So I know that any expectation using Monte Carlo estimation can be replaced with the summation divided by the number of samples. I samples from P data and then put it here. For the first term, I put, for example, I sample x1. I put x1 in the input of my network and generate an output and take the norm of that output and calculate the first term. For the second term, the gradient with respect to S of S theta of X. What is the dimension of this term? This is a vector. You take the gradient of a vector. The result is a d times d. The result is a Jacobian matrix. Okay? This is a vector, and you are taking the gradient of a vector. The output is the Jacobian matrix, d by d. Okay? Then I can calculate it. Why? Because I have this model, and I can use any libraries like PyTorch, anything to calculate the gradient, the gradient matrix, and then I sum the diagonal elements. So everything is, you can calculate it. Does it make sense? Why we can calculate it? Yes? Everyone, yes? Okay.
But why though?
Yeah?
Why?
Yeah, you will see. One of the most interesting works that Ivarinen and Dayan showed is that LESM and LISM are equivalent optimization objectives with respect to theta. What does it mean? If some very weak conditions met, they are equivalent objectives. We write it with this notation. They are equivalent objective with respect to theta. What does it mean? It means that if this term, for example, is theta 2, this term is theta 2 plus 10, plus something which is independent of theta. So the minimizer is the same. This is very important. The result is shown in that paper. We do not talk about how we can prove it, okay? But they prove that these two visually independent things are equivalent optimization objective. It means that if you minimize the first one, you are exactly minimizing the second one in terms with respect to theta, and vice versa. So, because the second one is more plausible for us, we minimize this one with respect to theta, and it means that you are minimizing the first one. Yes?
Wait, it's like the second, I just guess that it's the second one, like a Taylor expansion of the first one?
Yeah, you can use ideas from Taylor expansion here to talk about how they can be equivalent. But the equivalence, you can check this paper. They showed very, very simply how you can prove that they are equivalent. But you have some ideas from here, approximations, okay? And this is the important point that they showed. They showed that this one is really complex. Not complex, you cannot calculate S data. I cannot think of S data because I just have samples from P data. Very, very hard to think of S data. It's maybe even its form. But if you minimize this loss, where this part is independent of S data, you are minimizing this one with respect to theta. Does it make sense? So, from a very hard, even to calculate term, we derive a term which is at least you can calculate. Now we will see that how you can take the gradient, but you can calculate it. We see that how you can calculate the first term, the second term, and then take the summation, and then for several samples coming from the true data distribution, you can calculate it. So the absolute value is not, you cannot compare the absolute value of the loss, because there may be something like this 10, because they are not equivalent. They are equivalent, they are equivalent optimization objectives. It means that in terms of optimization, they are equivalent. It means that there are some parts that they differ, but those parts are independent of theta. Okay. So this is the first step, the first important step for energy-based, for score matching. Everything is clear? Okay. So how you can calculate the ISM? The ISM means that the implicit score matching objective. This second one. I also clear this part, but pay attention that they are equivalent. They are two equivalent objectives. I can easily sample from the data set and calculate these two terms. Is it clear how you can calculate the second term? Clear? Okay.
Just a question.
Yes.
Have you changed the slides? 'Cause
Yes, yes. Oh,
in the version I have, it's
maybe I do not upload it.
like,
I
will upload it.
no, sorry. I can upload it after the class. So sorry. Usually I upload it before the class, and today I forget. Sorry. Okay. We have these two. We can calculate the ISM, implicit score matching. The A is coming from the Monte Carlo estimation, and the gradient with respect to f, with respect to x of s theta of xn is a Jacobian matrix with dimension d times d. And we just need the diagonal elements. We do not need all the elements because it is the trace. So I need to calculate the diagonal elements. And we know that the I and j element of this matrix is calculated. You can calculate it using any of the methods you have in, for example, in PyTorch, and then you can calculate this loss. Just instead of the trace, I replace the summation over the diagonal elements. Nothing changed. Clear? Okay. And this is the score model score function. It means that s theta of x. It is modeled because you have theta here. Score function because you are working with score function instead of the density. The input is d-dimensional, the output is d-dimensional, and again, pay attention to the fact that you are completely flexible here. It means that you do not have anything to be met in the output. For example, sometimes you, in the case of VAE, in the output, you should estimate the covariance matrix. The covariance matrix should be positive definite. But here you do not have any limitation. Anything can be replaced, can be placed in these spots. CNNs, fully connected, RNN, transformer, anything. Just the dimension is important. Output and input are both d-dimensional. If you need the slides, I can upload it now. Does it?
There is a slide, but I think it's, for example, the previous slide in the version I have, it's like 49, but it's 15 years.
Yeah, maybe.
But generally, the
Transition. No, the transition are changed. I just add transition. I upload it now. Let me upload it now. I can easily upload. Think of score matching. Do you have any question? I think it is now accessible in the presentation, and the presentation, the transition, that will upload it there too. Yeah. Can you check whether it is updated or not? Yes.
Back to the previous slide. ISM. I'm just wondering, like, if you expand that ESM back one more step. Back one more step
Back.
To ESM.
This one?
Yeah, so that if you expand that, you sort of would end up with like some terms that are not dependent on theta and some that are. So I'm wondering, like, if you ignore the terms that are not dependent on theta, and some terms will just be dependent on some constants. In terms of optimization, it might still be equivalent, right?
Yeah, the idea here is almost similar to the fact that assume that in the KL, we see that if you expand the KL, then the terms related to the data, the entropy of the true data distribution will be deleted. Why? Because it is independent. The similar things happen here. Yeah. But it's a vector. It is a bit more complex than that one. That one was it was numbers. Here is a vector. Is it now updated in the website?
Yeah.
Okay. So we can continue. Pay attention to the fact that now I need to calculate these two terms. How I calculate it? The first term, I have a forward propagation. Pay attention. I have a forward propagation of the network. I input x here. At the output, I have s of x, and I can calculate the norm of the s of x. So I can calculate this term. For the second term, what happened? I have s of x. Now I should back propagate s of x, the first element, back propagate it, and find the first element here, the back propagation. Pay attention, it's back propagation. This value is the index 1 for this summation. This value is the first index in this summation, and then you continue it for the d times and calculate the last index in your summation. Do you see any challenge here? In terms of what?
It makes sense, first of all. It makes sense. My question is more of when you have a D by D matrix, in this sense, what they want to achieve is to have a vector representation that's in the same dimension. So, just in high level, when you take the trace, you are losing some information, right?
What do you mean? The thing that is important for us is that ISM and ESM are equivalent. It's hard to track where is the information, but we know that this approach is exactly similar to minimizing ESM, explicit score matching, which is a trivial loss function for score matching. The L2 norm in the area that are high probability.
Makes sense. My question is more of like, generally speaking, is the trace of a matrix a good representation of that matrix? Through the
trace, you will see all the weights here. It is not just limited to one path. You will see all of them, and they are all backpropagated. But you just use the first element. It means that the gradient of this one with respect to the gradient of this output with respect to the first input. This is the first diagonal element on the Jacobian matrix. The gradient of the first element of the output with respect to the first element of the input. This is the first element of the Jacobian, okay? But it uses all the information in between. And then you will follow all of these. It means that the second one is the gradient of this output with respect to this input. The second one is this output with respect to this one, and the last one is the gradient of the last element with respect to the last input element. So everything is playing its role. Does it make sense? It means that there are not some parts of the network that are not triggered through this backpropagation. All of them will be triggered, and all the information will be gathered using that summation. What is the result of this process? The result is just a calculation of the loss. You do not calculate the gradient yet. Does it make sense? Although you have gradient, you have backpropagation here, but the result is just the calculation of the loss. You do not have the gradient yet. Now you should start to get the gradient. But I want to know, in the loss calculation, do you see any complexity, any bottleneck for scalability, especially in this row? Yes?
Size of the input.
Yeah, the size of the input changes the number of backpropagation you need to calculate the loss. We do not talk about the gradient. The gradient is another problem. But even to calculate the loss, you need to do the backpropagations. It means that, assume that you are in the, example, 1,000 by 1,000 images. It means that you need 1 million calculation of this type to just evaluate your loss.
But you can do it in parallel.
Yeah, you can do it, yeah. But there are lots of these operations. And that is, let's say, challenging. Okay, let's talk about the limitation. The data score function is not presented in score matching loss function. Excuse me, the data score function is not presented in implicit score matching loss function. This implicit is missing here. Thus, one of our challenges is solved. The challenge that we do not know what is this S data of X. So that problem is solved. But we have a new challenge. And what is that challenge? It is that we need to compute the diagonal elements in the Jacobian matrix of S theta of X, which requires to call back propagation for D times. And this is really challenging. For example, for one data point, when you are training the model, you have lots of these calculations. And when each of them needs D backpropagation, it means that it is not scalable to high dimensional data. Does it make sense? Okay. For example, in the case of the image that with 224 times 3 dimension, you need to call this times backpropagation just to calculate the loss. It is not for the gradient, okay? And the gradient is also another problem. So score matching, even the implicit score matching is not scalable with the dimension of the input. But we know how to calculate it now. And then if you can calculate it, it means that you can take the gradient. Does it make sense? Because you may take the gradient by yourself, or you give it to one of the libraries and it calculates for you the gradients. Okay? So we find one solution to score matching, but it is not scalable. But it is a solution in contrast to explicit score matching. Because explicit score matching, even you cannot calculate and calculate the loss value because you do not have this S data of X. Okay? The solution to this problem is denoising score matching. Pay attention to this denoising version. It's a very nice approach to solve the problem. Assume that I have a noisy version of my input. I have images, but by myself, I generate a noisy version of those inputs. How? By adding easily by adding a Gaussian noise to the data. Then the conditional distribution of X tilde given X, also known as a smoothing kernel or noise model, denoted by this Q sigma X tilde given X, is this one. It means that the adding noise process can be done using this conditional distribution. Is it clear? It means that you have a new noisier version. The noisier version is exactly your data point that is added a noise with this variance to it. It means that the bias is your data point, the variance is sigma 2 times I, and then you have a distribution for the noisy version. Does it make sense how we generate the noisy data? So, for the data set, I generate a noisier version. It means that if they are images, I have noisy images. Then the level of noise is dependent to this sigma. Okay? Yes?
So this distribution is just for one data point here. Yeah, and X as a one data point.
The things that I write it here, yeah. But in general, you can define the distribution for your noisy data.
So how is it possible? Like, what could be the figure?
Yeah. Assume that I have the cloud of my training data set here, and then I add the noise to each of the points. And then remove your data set, you have a new cloud. That cloud represents the distribution. That distribution is Q sigma of X tilde.
So the Q sigma here is the summation of the whole normal distributions over each data point.
No. Do not pay attention. When you let me talk about. Look at this picture, okay? The red curve here. The red curve is your data, okay? The red curve is your data. When I add that noise, because this is a mixture of Gaussian, it is simple to generate the formula of the data at the noisier version. You can take it in the closed form, okay? When you add the noise, based on the variance, you have the blue, this dashed blue, this one. It means that it's spread. The peaks spread based on the sigma value you use. Okay, this is the result of how in the cloud. Again, the cloud expand. The cloud of data points will expand.
The sampling from the noise would be like this, but my question is how, because this Q is the summation of like multiple Gaussian distribution. Because for each data point, we have a Gaussian distribution. So yeah, think of it, how is it so smooth? How is the distribution of the Q? How is it so smooth?
Each point previously, think of degenerated case. Assume that the original data is something like this. What does it mean? It means that it is coming from the normal distributions. For example, this is 1. We mean 1 and variance 0. What happens if I apply this noisier version? What are the probable points after applying this?
The mean would be the same, but with like higher or lower.
Yeah, something like this. So it's spread. When the original data is condensed, is compressed, when you apply this noisy version, it's spread. It is spread exactly symmetrically around the mean. Yeah, but think of it in the general case of your training data.
No, I get it. So my question is that this formulation that you know,
Which of them?
this one is for only one data point, not the whole distribution.
Yeah, this is for X. For X, for one data point X, then, but you can think of X as a random variable. And then you can write this formulation. That, if you have the joint over X and X tilde, you can integrate out X, and then generate the distribution over X tilde itself.
And this is what you have like plotted in the next two slides. Yeah.
This one?
Yeah, this is the integrated version.
Yeah, this is the output of the integration. Yes. Because it is Gaussian, the output can be calculated in the closed form. But in general case, you cannot calculate it.
And the output of the integral is also Gaussian?
Yes. The input is mixture of Gaussian, the output is also mixture of Gaussian, just the variance is increased. Yeah. Okay. Any anyone have any question about this noisier version? What happened to the data when we have? Just think of it in terms of distributions. Not the isolated points is very good for this part, but for the unconditional distribution, think of it the distribution. All the data, all of them are the noisier version. You have a new cloud of points. That cloud of point is representing a new distribution. That new distribution is Q sigma x tilde. This is the formulation for that new distribution. Yes?
Is the point to sort of replace P data?
Yeah, you will see that we will work with, instead of x, we will work with the score of this function, this distribution, sorry. And then you will see that that trace will be eliminated from the calculations. Okay, any question? Okay. So I have a new distribution, Q sigma of x tilde, and it is a function of a parameter. It means that if I change sigma, I have a new distribution. Intuition. Each sample of x tilde is the result of adding Gaussian noise to a Gaussian random variable to sample x from the data distribution. In the limit term, if the sigma is approaching to 0, then the added noise converts to 0 constant, and when we expect the two distributions to be similar to each other. It is trivial. If sigma approaches 0, you can update this integral, and you will see that this will be a delta. This is a delta function, and then the p data will be sent out from the integration. Okay, so we know that if the sigma approaches 0, we have equal distributions. So for a small value of 0, we can assume that they are equal. For a small value of sigma, we can assume that this q sigma is equal to the p data of x. They are similar distribution to some extent. Now pay attention to the example that we talked before. I have assumed that my true data distribution is the mixture of Gaussian, okay? This is very important. If your true data distribution is a mixture of Gaussian, then you add this noise to your data, then just the variance of those Gaussian will be changed. For the Gaussian, you can have it in the closed form, but in general, you cannot derive the closed form for this Q sigma of x tilde. Okay? Just the mean is not changed, just the variance is increased. Okay? So, we see that if we have a distribution, we can make a noisier version of it. And in the case of the Gaussian, we can have the closed form for the noisy version. This is the original data, this is the noisy version, and this is the result. I have 0.4 times this Gaussian and 0.6 times this Gaussian. This is the red curve, and I start to add noise to my true data distribution, which is the red curve, and the result is the Q of 0.1, 0.5, 1, 2. And you can see that when I increase the variance, the distributions becomes smoother and smoother in terms of fluctuations. Is it clear how? Now it's scale it in the higher dimensional space. This is just one dimensional, it's very hard, but scale it. Yes?
Can we have a score functions for discrete values, not the continuous?
You know, the concept is coming from the gradient with respect to x, which means the x to be continuous. Does it make sense? What happened in the high dimensional? In the higher dimensional, the cloud will be expanded, the cloud of the point. It means that, assume that each point in the original, the true distribution is exactly a point. When you have a noisier version, it can move around the previous point a bit. And the distance that it can take from its original place is dependent on the sigma. If sigma is large, it can easily escape from its original point. Does it make sense? Okay. as we see before, for sigma approaches 0, the marginal distribution, the Q sigma of x tilde approaches the true data distribution P data. We can think of matching the model score function to a score function S sigma associated with Q sigma. Now we want to introduce another loss function. Previously, we want to match S theta to S data. Okay? And these two loss, we see that these two loss can do this one for us. But the problem is that this one is hard because you do not have any formulation for S data. This one is easy to calculate, but in terms of complexity and resources to calculate, it is challenging. So the second one has also some problems. Now, I claim that I can replace this data with sigma. Instead of fitting your model to the true data, fit it to the noisier version of data. Then you have a parameter to control. What? What is the parameter? What? Yeah, the variance. The variance of that noise. You can, instead of you can assume fit it to the data with variance of 0.1. It may not be a good option. But there is a control value here. Maybe you can apply to this one. This is a very small value, and maybe it is exactly similar to your data. So if you can match the model distribution to this one, it's a good option if it can mitigate the challenge here. But we should check whether it increases your challenges or not. Okay? Just think of this new approach. From data to S of data to S of sigma. Okay? This is what we will talk about in denoising score matching. We can think of matching S theta to S sigma when we know that. What is S sigma? What is S sigma? S sigma is the score function of the noisier version of the data. We know that both of them are not accessible. Not the score function of the data and the score function of its noisier version. They are not accessible, but we want to fit our model to this S sigma. And this is a new definition. L explicit score matching of sigma. Why it is explicit? Look at the form. Why is it explicit? How we define explicit and implicit? Explicit means that you are calculating with respect to score functions itself. You are not using that trace. What is the problem with this formulation? With this loss? There is a problem. There is a similar problem that we have seen before. Can we calculate it? Why? Yes. Similar to the fact that we do not have access to S data of x, we do not have access to S sigma of x. So I just replace x tilde here, just for the fact that we know that this is the noisy version. You cannot calculate this loss because you do not have access to S sigma of x, because it is the score function of the noisier version of your data set. So you do not have access to it. Similar to the S data. But Vincent defined denoising score matching loss as this. This paper is also a great paper. Yeah, I highly recommend to look at this paper, and it is very well written in terms of mathematics. The denoising score matching, it has a subscript sigma because it is based on the noisy data of theta. Yeah, of theta equals the expectation over the joint. You do not have any idea how they are related, okay? Just pay attention that it is a new loss, and you can calculate, check that whether you can calculate it or not. What do you think? That term, that gradient, do you think you can calculate it or not? What is this conditional? What is this conditional?
Condition.
No. What is the formulation for that? We know that how we add the noise with the Gaussian. That conditional is Gaussian. If you have access to X, this is a Gaussian. And what is the gradient of the log of the Gaussian? It is a very simple form. It has a very simple, we see at the start of the course, when we talk about the score function of Gaussian, it was x minus mu over sigma, something like that with a minus sign. Do you remember? So, the first term was very simple. The second term also becomes simple. But we do not know how this one is related to this one. This is just a loss that Vincent defined. Yes.
Is Q sigma P data but
Q sigma, this one, this is the kernel. It means that it's conditional. This is not the marginal distribution. This is the conditional distribution. It means that exactly this form, this one, yeah. This is exactly this one. This is not a conditional distribution. The simplicity comes from here that when you take the gradient of this term with respect to x, you have a very simple, the log of this term. Excuse me. When you take the gradient of the log of this term, you have a very simple term that replaces your trace.